All right, everyone, I'm going to go ahead and introduce our speaker today. Today, we're going to have Óscar Carrión-González giving a talk on unveiling the atmospheres of cold and temperate exoplanets with direct imaging observations. Óscar did a MSc at the University of the Basque Country and then defended his PhD in 2022 at Technical University of Berlin, and he's now a postdoc at Paris Observatory. He works on direct imaging techniques for the observation of cold and temperate exoplanets and also studies solar system planetary atmospheres as a way to prepare for those observations. He's on the Roman CPP team, and he's also a member of the Life Initiative. And he has a couple papers out there that I think a lot of you would be interested in if you get a chance to take a look. Óscar, go ahead, take it away.
Okay, thank you very much. So I'll be quickly talking about the work that I started during my PhD thesis in Berlin, and that I've been continuing as a postdoc at the Paris Observatory in France. So I'm interested in everything cold, temperate planetary atmospheres, in particular those of the exoplanets that we have not observed yet. We know there's an interesting population of cold and temperate exoplanets out there. We have discovered quite a few already, mostly with radial velocity techniques. But yeah, transit so far has been the most fruitful technique in terms of exoplanet discoveries. So actually, we're kind of biased due to the technology available towards characterizing the atmospheres of cold and temperate hot planets on short period orbits, and therefore cold and temperate exoplanets are a population that we cannot access right now. We know there are many more in these 1 AU orbits that we'll be discovering with Espresso, Camenes, and some long baseline transit missions. We really want to understand the atmospheres of these planets, but we really need direct imaging observations. Like transits are not very likely. All this outer region is very unlikely to produce a transit. We are currently observing the inner population of exoplanets, but temperate ones around solar-like stars and cold Jupiter analogs are out of reach so far. This is a bit of a basic introduction, but I think it is worth to mention that direct imaging will be the technique to actually characterize this population of planets by either blocking the stellar glare with optical devices such as coronagraphs or star shades, or by using optical techniques such as nulling interferometry, and I'll discuss a bit more about that later on. So at the end, we will have an inner region blocked together with the star, which will not be accessible, and an outer region that will be out of reach as well. So we'll be observing exoplanets in this field of view, given that they're brighter than the minimum contrast. The interest for direct imaging technique dates from a while ago, but recently both the ASTRO 2020 Decadal Survey in the US and the ESA Voyage 2050 Senior Committee report in the EU have actually driven the priorities for astrophysics in the coming decades. And direct imaging in both cases is a priority for actually getting to observe this population of exoplanets that have remained out of reach so far. In the US, you already know that we will have the Habitable Worlds Observatory capable of observing Earth-like planets around Sun-like stars in reflected starlight. On the ESA side, they recommend the participation of European institutions in the development of this instrument. Back then it was either LUVOIR or HABEX, but ESA has recently opened a call for European participation on Habitable Worlds Observatory as well. But they also recommended as an ESA topic itself, the characterization of temperate exoplanets in thermal emission. So actually by means of direct imaging observations in the mid-infrared. They acknowledge that the technology required to do that is still being developed. So they recommend the European community to develop a feasibility study. In particular, they mention if it is found that at least 10 temperate exoplanets can be characterized with such a mission, and thus a scientific breakthrough can be achieved. Then the committee actually recommends this topic as a scientific priority for a large class European mission in the 2050 timeframe. So actually there's apparently quite a bit of an interest about this, and this sets a direct imaging timeline for the coming years and decades in which we will have Roman as a technology demonstrator in the mid-2020s, in 2026, 2027, which will actually change our current idea of direct imaging observations, which now means observing young luminous giant exoplanets in emitted light. Roman will actually enable the observation of Jupiter analogs, maybe some super Earths or mini Neptunes in case of an excellent performance, but that is not something that technology demonstration requirements is set to achieve, but it will set the path for next generation of instruments, both on the ground but also in space, such as habitable worlds or this large interferometer for exoplanet mission that I'll discuss a bit about later, which will allow us to directly image Earth-like planets around Sun-like stars, and potentially both in reflected and emitted light. And I'll go back to that at the end of the talk. So there's an exciting a timeline ahead, right? But we have to make sure we understand the physics of these observations before, so we can understand the science output of direct imaging observations. And in particular, during my PhD thesis, I studied the science output of direct imaging observations in reflected starlight. So I'll be addressing a few questions that I asked myself back then and during this postdoc year at the Paris Observatory about first, what information is contained in the reflected starlight spectra of exoplanet, and then what is the best way to actually retrieve the information. And finally, we want to go to the real world and know the actual targets that these direct imaging facilities will be able to unveil and to characterize. So in order to answer this question about the information content on reflected starlight spectra, we used retrieval exercises. We have no direct imaging observation in reflected light, so we have to simulate ones. We given an atmospheric model of an exoplanet, we produce a synthetic measurement, and with that we try to infer back the original properties of the atmosphere by means of a sampling methodology to get to understand the correlations between the different parameters, the uncertainties at the time of observing such a cold or temperate exoplanet. And for that, well, let me just quickly mention that when we talk about reflected starlight spectra of exoplanets, we generally provide them by this planet to star contrast ratio, which involves both atmospheric and non-atmospheric parameters, and that'll be interesting, as I'll show you in a second. We have the planet radius, which will, of course, plays a role in the brightness of the planet. We also have the distance to the star, which gives us an idea on the number of photons that arrive to the planetary atmosphere and then might get scattered back to the observer. And then we have these properties of the planet itself, such as the geometrical albedo and the scattering phase function. And there's a lot of physical information contained in the scattering phase function. It depends on many things. It depends in the physical properties of the atmosphere, in the observing geometry, given in this case by the star-planet observer phase angle. So there's actually a lot of physics going on here, mixing atmospheric and non-atmospheric parameters, which might condition this spectra of exoplanets in reflected starlight. To simulate observations and to carry out the retrievals, we use a pre-existing relative transfer code presented by Garcia Munoz and Mills, 2015, which is very, very versatile. Actually, it is able to perform many more things that the ones we use. It supports polarization measurements, non-uniform atmospheres such as cloud coverage, non-uniform surface with different albedos. It has been thoroughly tested in solar system planetary atmospheres and also on exoplanets. The important thing here, it is a multiple scattering relative transfer code, and that will allow us to accurately model the behavior of light when it interacts with the planetary atmosphere at different observing geometries. And that will play a role, as I'll discuss in a second. That will be very important to actually accurately modeling the multiple scattering processes that the photons undergo in the atmosphere. The model that we introduce in our study is built upon solar system observations. We assume a gaseous atmosphere dominated by hydrogen and helium, with methane as the only absorbing species for the moment, and one cloud layer. And this general structure is consistent with the upper atmosphere of solar system planets, from Jupiter to Neptune. At some point when running these retrievals, in which again the goal is to understand the physical correlations between the different parameters that might play a role when getting to observe an exoplanet, we have to keep a balance between building a model that is complex enough so that is physically meaningful, and building a model that allows us to understand the different effects of the different parameters and the different correlations. So if the atmospheric model is over parameterized, we can get to some either overfitting problems or problems in which situations at which we cannot understand the different contributions of the different physical parameters. In this case, the cloud, which will be also very important here, is characterized by its optical thickness, its position in the atmosphere given by the optical thickness of gas above the cloud, and also its geometrical extension in terms of the atmosphere of the atmosphere's scale height. Then the aerosols are modeled in terms of their radius and their single scattering albedo, and this will provide us with the scattering phase function of the aerosols at the different observing geometries. Finally, we add methane in the atmosphere, and we add the planet radius as a model parameter to be included in the retrievals, and that's new with respect of most of the works that were being performed for these retrievals of direct imaging observations of exoplanets. So actually, we wonder how important it is to include the planet radius in the retrievals. I mean, we had some papers about, say, or getting to directly image a Jupiter at 10 parsecs, but why if we don't know if it's a Jupiter? Like, direct imaging observations will be just a pixel of information, and we might not know if that pixel is bright because the planet is big, or it is bright because the clouds are very reflective, or because of other combination of reasons. So we published a paper on that back in 2020, in which we perform atmospheric retrievals for different cloud scenarios of an exoplanet to be observed in direct imaging. I'll just show you here the results for the thick cloud scenario, which are particularly interesting, as they allow us to observe the degeneracies between all the cloud parameters. I mean, these plots are interesting, but I think there's too much information in here to be detailed in this talk. Let me just say that these corner plots, with both assuming the planet radius to be known and assuming the planet radius to be completely unknown, this corner plot shows us the retrieval results compared to the true injected values, which are these green lines in each of the subplots for each of the atmospheric parameters, and also here for the planet radius. And I'll focus on the two parameters that I find are more striking here, maybe, which are the methane abundance and the optical abundance of the cloud. That is the optical thickness of the cloud. And you can see here that if the planet radius is assumed to be known, and that is not playing a role in the retrievals, we can more or less constrain the abundance of methane pretty well. We can also constrain the optical thickness of the cloud. Maybe we cannot set the exact constraints that we injected, but we can at least get a sharp lower limit on the optical thickness of the cloud, meaning we know there is a cloud in that planet. We know that's a cloudy exoplanet. We might just not know the actual optical thickness. But if the planet radius is unknown and it is included in the retrievals, it will trigger many degeneracies between the different atmospheric parameters. And in particular, it will be highly correlated with the optical thickness of the cloud and the other optical properties. And you can see in the retrievals of the optical thickness of the cloud that the retrieval result is almost flat, meaning we cannot distinguish in practice between cloudy and cloud-free exoplanets once the planet radius is completely unknown. Also, the methane abundance retrievals degrade significantly. And that is an important result. We discuss it in more detail in the paper, but we also tested how different radius uncertainties can help us improve the retrieval results. But in the two extreme cases, when the planet radius is known or when it is completely unknown, we see significant differences in the retrieval results. So even if it is not an atmospheric parameter itself, the planet radius will play a role, and this will be relevant for direct imaging observations of exoplanets in reflected light, because most of these targets will be discovered in radial velocity, so we will actually have no measurement of the planet radius. Of course, we will be able to do some educated guesses on some of these planets. Maybe if it is a one mass, like one Jupiter mass planet, we can guess it is a one Jupiter radius planet. But as we go down to the super Earth or mini Neptune mass regime, this will have or might have a bigger impact. So this is just some extreme cases in which we assume no prior knowledge on the optical properties of the clouds, that is the cloud composition at some point, and no prior knowledge on the planet radius. This has an impact actually. So next question was actually how to improve this, like which observing strategy can optimize these atmospheric retrievals if the planet radius is unknown. And in particular, we tested how observing an exoplanet at multiple phase angles can help us with that, because we know that aerosols do not scatter light in the same way in all directions. So actually, by probing directions, one might expect to get different information about the planetary atmosphere. So this has been studied before for solar system planetary atmospheres. Of course, this is not new, but this has also been studied for exoplanets as well. But in the paper that we published in 2021, we discussed some of the difference with previous works published in the literature, and we use our model from the study I just showed you to work on atmospheric retrievals if the planet radius is unknown, in order to understand the degeneracies at the different phase angles at which we can get to observe a planet in direct imaging. We carry out single phase retrievals, just like before, single observations in direct imaging of reflected starlight at different orbital geometries, something close to full phase at 37 degrees of phase angle, something close to quadrature, and a rather high phase angle of 120 degrees, just to try to understand if there's meaningful differences in the retrieval results. And although we find some differences when the phase angle is rather high, 120, we find that single observations do not get to constrain the atmospheric properties of the planet if, again, the planet radius is unknown. Single phase retrievals cannot break these degeneracies. But on the other hand, if we adapt our retrieval methodology and we combine the information of different observations, we carry out multi-phase retrievals, as you can see in the bottom row here, things get better actually. If we combine observations at phase angle 37 and quadrature in these blue lines in the retrieval plots, well, actually we don't get that much of an improvement. But if we combine observations at small and high phase angles, that is about 40 and about 120, it really gets better. That is both the red and the black lines in these plots. We can go back and retrieve more or less an accurate constraint on the planet radius. We can also get this sharp lower limit on the optical thickness of the cloud, meaning we can say it is a cloudy exoplanet. We retrieve the methane abundance pretty well. And we can even start constraining other optical properties of the aerosols, such as the single scattering albedo and even the pressure level, so to say, of the cloud a bit better than if we only combine observations at 30 degrees and quadrature. And the reason for this is actually that we are probing both the backward, the forward and the backward scattering components of the planetary atmosphere of the aerosols in the cloud. So this allows us to start breaking all these degeneracies between the brightness of the cloud, the size of the planet, and the reflectance of the and the abundance of cloud aerosols. So I have some backup slides on this. I can show you later. I'm not going into the details, which are in the paper, by the way, but we tested this and we found that it is actually probing the backward and forward scattering components of light interacting with the atmosphere, which helps us improve the retrievals in dark image observations of exoplanets in reflected light, right? Next question, obviously, was to understand how many of the planets that we know are suitable for such multi-phase direct imaging observations, and overall, which of the known exoplanets are suitable targets for future direct imaging facilities. So for this, let me just go back and mention these three rule of thumb criteria that I mentioned before, by which we will be able to directly image an exoplanet if it is orbiting at some point beyond the inner working angle of the instrument, say a coronagraph, and within this limit defined by the inner and the outer working angle, and also provided that the planet is brighter than the minimum detectable contrast that the instrument will be able to detect, right? So we developed a statistical methodology by which we download the whole NASA exoplanet archive, and we run for each exoplanet thousands of orbital simulations by letting at each realization, or letting each relevant parameter vary within the reported upper and lower uncertainties. And once we have all these orbital simulations, we apply the detectability criteria of a given direct imaging facility, so we can get an output catalog of detectable targets, or say potentially detectable targets, of course. And this was also published in a paper back in 2021, in which we presented this methodology and we applied it to the Nancy Grace Roman Space Telescope. And of course, let me say that the results in here were obtained with the data we knew about the coronagraph performance back in 2020. So things have changed slightly, but I think it is worth to discuss a bit about the statistical method itself, which is generally applicable, and also about the results that we got for Roman, and I'll show you later. We also applied it to other direct imaging facilities. In summary, at each orbital position of each orbital realization that we simulate with this code, we check the brightness of the planet, that is the planet to star contrast ratio, and the angular separation between the planet and the star. If both meet the criteria of the specification, so to say, of the facility that we are studying, we say that this planet at this orbital position is accessible to direct imaging observations in reflected starlight. So we do this for each of the thousands of orbits that we simulate for each exoplanet. And let me just say that the theoretical setting for this is rather simple. We use Keplerian equations of motion. Of course, we have to take some assumptions. I discussed before about how complex planetary atmospheres are and all the things that can condition the brightness of the planet, right? But here we cannot build atmospheric models tailored for each of the 5,000 exoplanets. So we just assume generally geometrical albedo 0.3, bone albedo 0.45, and Lambertian scattering, which is fair enough for massive calculations of 5,000 exoplanets. If we want to go into more detail for a particular one, we can give as an input here other brightness criteria, more physically realistic, so to say. Let me also just say that the code itself is compatible. It supports some missing orbital parameters, which generally exist in the NASA Exoplanet Archive, because not all of the exoplanets have a constraint on the orbital eccentricity, on the orbital inclination, on the argument of periastron, and also on the planet radius. I just mentioned that all of the most of the interesting targets for us are radial velocity targets. So in case we are missing some of the orbital parameters, we assume like random orientations of the orbit at each orbital simulation. So at each of the thousands of orbital simulations that we run for a planet, we draw random values from these intervals here for the eccentricity, inclination, and argument of periastron. And once we have the mass of the planet, we compute its planet radius if it is unknown by means of the mass radius relationships in Hutses and Rauer and in Otegi et al. 2020, both for giant planets and for low mass exoplanets. So we produce several outputs which are relevant for the detectability analysis themselves, but also we produce some other outputs that might be relevant for atmospheric modeling studies. The most important figure here that we produce is the probability of a planet to be accessible, and that is just the number of runs that the planet is potentially accessible, divided by the total number of runs that we run. Typically for this paper, it was 10,000 runs for 10,000 orbital simulations for each exoplanet. But then we also provide the range of observable phase angles that are detectable with that direct imaging instrument, and also the equilibrium temperature change throughout the orbit, and in particular the regions, the detectability windows, like the equilibrium temperature at the windows where the planet is detectable. And this would be informative of how much the temperature of the planet might change throughout the orbit. We have quite a few eccentric planets for which there are significant changes in the equilibrium temperature, and this might be driving some interesting atmospheric processes, which we will be happy to model when we get to observe these exoplanets. And finally, when we applied this to Roman back in 2020, we compute all these for 3 coronagraph scenarios, 3 possible performance scenarios that were reasonable back then and which are not super crazy right now either. So we had this optimistic, this intermediate, and these pessimistic scenarios, and here you have the values of the inner working angle, the outer working angle, and the minimum detectable contrast. And all these we run again for 3 different filters, the 3 possible photometry filters that Roman might be available to observe at 535 nanometers, 730, and 825 nanometers. So we provide the probability of a planet to be accessible and the range of observable phase angles at each of these filters. I can show you an example of the table that we produce later if you're interested. So the main results of this was that up to 26 of the known exoplanets were potentially accessible to Roman. Those are planets accessible in the optimistic coronagraph configuration. Then in the intermediate and in the pessimistic case, this figure drops to 11 and 3 respectively. And let me just say that these numbers are the planets with a probability to be accessible greater than 25% in order to be somehow meaningful, with host stars brighter than magnitude 7. And I know the requirements for at least the tech demo phase of Roman are a bit different now, with magnitude 5 being kind of the safe value for now. This can be rerun, and we could get some some new results with that, but these were the criteria that we were setting back then. Just an example of the type of plots that we produce for two particularly interesting planets. These are the probability of the planet to be accessible in the optimistic configuration of the coronagraph. These are Tau Ceti E and F, which are two super Earths in the boundaries, in the inner and outer boundaries of the habitable zone of these nearby sun-like stars. So these are actually the results that we are computing. Each line in here, each black line is a simulated orbit in which we can see the planet getting farther away from the star. Here you have the angular separation between the planet and the star, and also the planet getting dimmer and dimmer as the phase angle increases. You have also here the planet to star contrast ratio, and here we have the range of observable phase angles with that configuration of the coronagraph. And finally, as I mentioned, we also produce the changes in the equilibrium temperature of the planet, which is each of these black lines, and the detectability windows, which are given by this green color for each line here. Okay, so overall, population-wise, we find that actually the population of planets that are potentially accessible to Roman are significantly different than the ones that have been accessible to atmospheric characterization right now, which are these transiting planets that I plot here from the NASA Exoplanet Archive. You can see that the equilibrium temperatures of these transiting planets are way higher than the ones that we will be able to reach with Roman. So Roman, of course, is a technology demonstrator, but in case it performs excellently well in a potential science operations phase, it will be able to reach a population of planets that was not accessible for atmospheric characterization right now. So I think that is exciting, and that also set us the next obvious question, which is, okay, what about the next generation of missions? And we have, as I mentioned before, we have several of them after Roman. Roman will be of course, the technology demonstrator for the Habitable Worlds Observatory, which is currently being designed, right? And then we also have in the as a response to this ESA 2050 Senior Committee report, we have this large interferometer for exoplanet mission concept, which will aim to observe to directly image low-mass temperate exoplanets in emitted light, that is in the mid-infrared. And both Habitable Worlds and Life will aim to answer the question of how unique is our Earth, how unique are the atmospheric properties of the Earth for equivalent mass planets at equivalent insolation levels, and ultimately how unique are the habitability conditions in our planet. And the complementary wavelength ranges of habitable worlds in Life, visible near infrared and the mid infrared, will actually help us in answering this question from different points of view. And I'll discuss in a second how we can profit from multi-wavelength observations, right? This is again not new. This is a question that dates back to this old TPFC and TPFI concepts by NASA, and also this Darwin concept by ESA that were developed in the 90s and that were canceled soon after the 2000s, the early 2000s. These were very exciting missions aiming to directly image Earth-like planets around Sun-like stars, potentially. One of the problems was we knew no exoplanet back then, so it is important actually to now that we know more than 5,000 exoplanets, it is important to show that similar concepts right now could observe several already pretty exciting targets. And for that we published another paper within the Life mission in collaboration with some habitable worlds colleagues, in which we computed the detectability of known exoplanets, both with life and with the notional design of the habitable worlds observatory, and we discussed their synergies in terms of the science output when we get to observe the same exoplanet with both missions. We applied the same methodology as before, so I'll not describe all the methodology again. This is the same methodology as in our 2021 paper for Roman. I can go into more details later if you're interested on that, but let me just go ahead and show you the results we find. We restricted ourselves to the population of known exoplanets within 20 parsecs, which we should expect to be the prime targets for atmospheric characterization. And we find that, first of all, that current observational biases are playing a huge role in this plot, because so far low mass temperate exoplanets around nearby stars have been detected orbiting around M stars, and therefore they're orbiting at very small angular separation, and therefore a coronagraph is not tailored to get to observe those planets. It will not be the main goal of the Habitable Worlds Observatory. The Habitable Worlds will aim to observe sun-like stars and characterize their habitable zone, right? So when we're watching these plots, and sorry, let me just briefly describe them. We have this mass against orbital separation plots, in which we have some horizontal lines which indicate in blue the mass of Neptune, in green the mass of the Earth, and in red the mass of Mars, where we can find that life is performing really well at detecting most of the low mass nearby exoplanets that we know as of today. And that is because, again, they are orbiting around M stars with very small angular separation, for which annealing interferometers such as LIFE is very efficient at detecting these very nearby planets. On the other hand, habitable worlds is sensitive mostly to the long period exoplanets, and due to the again observational biases also of the radial velocity sensitivity limits right now, long period exoplanets are generally very massive. So hopefully with a bit longer timescales for radial velocity observations, we will get some more points here in the low mass long period regime, but also these missions themselves in a potential first search phase will be able to find many more of the exoplanets that we know should be there according to occurrence rates, but we have not been able to discover so far. Nevertheless, even taking into account these observational biases, we have already an exciting population of overlapping targets, about 50 targets which could be observed both with habitable worlds and with life if they're launched today. You can see here that they're generally in the super Earth to mini Neptune mass regime, and all the way to very massive exoplanets. So we have again some interesting targets with equilibrium temperatures similar to that of the Earth. We have again Tau Ceti E, we have Tau Ceti F, Tau Ceti H. So we have some interesting super Earths that could be observed with these two missions right now, but we know the list of common targets will just keep increasing, and we will have many more in this particularly exciting mass and equilibrium temperature range. Nevertheless, also we have a huge population of planets which is only detectable by life, and you can see here that they're mostly orbiting around M stars and K stars, and we have quite a few of them in the equilibrium temperature range of the Earth, and also with mass regimes close to that of the Earth as well. So life is quite sensitive at detecting known rocky temperate exoplanets, which is another way to say life is very sensitive at detecting temperate exoplanets around M stars, as well as around G-type stars. It just happens that we have not discovered such low mass temperate exoplanets around solar type stars. But we have quite a few interesting habitable zone exoplanets detectable with life, and some of them are also detectable with habitable worlds. So this is a bit of a busy plot in here, in which I am showing all of the planetary systems in which we have a habitable zone planet detectable with life. Detectability with life is given by these green dots, with black dots, for instance, here or here, meaning they are not detectable with life. White inscribed star markers indicate that these planets will also be observable with habitable worlds in reflected starlight. And of course, the size of the marker, both for the star and for the planet, is proportional to their size. So you have here the solar system as a reference. Okay, we see we have quite a few temperate exoplanets. Not all of them are in the rocky regime, of course, but we have a very interesting set of diverse sizes and diverse insolation levels, which could be already characterized by life mostly. I'm very interested about these planetary systems for which we have multiple exoplanets, both inside or outside of the habitable zone, that are all detectable with life. That this means we could study all of the different planets at different insolation levels and get to learn quite a few things about greenhouse effects and the evolution of planets with different insolation levels in the same planetary system. So that is quite exciting. I'll just mention the figure that these are 38 life detectable habitable zone planets, and we also run this study for different performance scenarios of life. I'm showing the reference one, and you have all the details in the paper. But even in the pessimistic life scenario, we can detect right now 33 habitable zone planets. So that is great. And you can see again that we have a bunch of them, and many of them orbit M-type stars. You have here Proxima, for instance. Some of them are very well-known planets. Some of these, like for instance, T-Garden, B and C, which are some of the planets with the same similarity index to that of the Earth. So pretty exciting targets. Good news is we will get many more coming in the years that are ahead before the launch of the habitable worlds, and hopefully the life mission as well. But the fact that we can already characterize some of these exoplanets with both wavelength ranges is absolutely exciting, because there's the science we can get from simultaneous or from complementary observations from life and habitable worlds. The total output there is greater than the sum of the individual scientific results that either hub worlds or life could alone obtain. So we know the reflected light regime is very sensitive to cloud properties, and that is great, because characterizing clouds in planets is very important. But it is also a pain, as I've showed you before in the retrieval exercises. There are many degeneracies between the cloud optical properties and all of the other physical parameters of the planet. So we really have to pay attention to that. If we're able to overcome all of these degeneracies, reflected starlight observation will be able to key features showing potential habitability, such as the ocean glint of a planet and the vegetation red edge. But on the other hand, life or mid-infrared direct imaging mission is able to accurately measure the planet radius because it is not very sensitive to the cloud properties. And this will also allow us to derive pretty well the pressure temperature profile, potentially down to the surface in some cases. And this mid-infrared regime is particularly sensitive to important molecules relevant to astrobiology, water, CO2, methane, ozone, and so on. But if we combine both observations for the same planet, we will be able to break all this radius albedo degeneracy. We will be able to obtain the wavelength-dependent albedo of the planet, its full energy budget, and potentially search for signs of a greenhouse effect. So the scenario in which we get life and habitable worlds flying is really exciting. So just I could end up with this. Let me just give a brief summary of the talk because it's been a bit long. So let me just go back to what I told you before. We found some important correlations when carrying out atmospheric retrievals of a directly imaged exoplanet in reflected starlight, and these correlations between atmospheric and non-atmospheric parameters are triggered by an unknown planet radius. This is relevant because we will generally lack a measurement of the planet radius for this type of directly imaged planets, but we also studied potential ways to improve the retrievals to overcome at least partially these degeneracies. In this case, multi-phase observations at both small and large phase angles by allowing us to probe the backward scattering component and the forward scattering component of the aerosol. And then to be able to know where are we going to be able to apply all these retrieval techniques, we built catalogs for direct imaging facilities. We developed a general purpose statistical methodology, and then we applied it to Roman and to notional designs of habitable worlds and life, and work is still ongoing to apply it to other facilities. So indeed, in this outlook, let me just say that there's a lot of work to be done, and the fact that we've developed some general purpose tools such as this retrieval technique and such as this detectability code, well, it will allow us to keep building on this because there are many interesting questions to be answered about direct imaging of exoplanets, of cold and temperate exoplanets, in particular in reflected starlight, right? So there are quite a few more questions to be asked, and hopefully we'll be getting the answers in the coming years. So thank you very much for your attention, and I'll stop here and I'll take questions if you have any.
Awesome. Thanks. Thanks, Oscar. You covered a lot of really, really interesting stuff there. Feel free to raise your hand and you can ask Oscar a question. Otherwise, if you'd like to just type it into the chat, I'm also happy to talk about that. But Oscar, thank you for a great talk. So if people are shy, I have plenty of questions, but I will, I'll try to hold up on those. All right, so I will go ahead and ask something real quick, Oscar. So for that first study that you did, where you kind of looked at detectability for known exoplanets, you probably have kind of phase space maps too then, right? I mean, I can imagine you can do this for all of the local stars where we haven't detected things yet and say, hey, this is where I would be sensitive to a certain brightness, eccentricity, inclination, all that other stuff, right?
Absolutely. That's a possible way to use this detectability code, which is to use it to find the boundaries, like the regions where we could detect exoplanets and the sizes or the brightness that we would be able to detect. Actually, there's this target star catalog for hub worlds that was published recently, and they're doing something similar to that, which is checking for which nearby stars we would be able to detect the habitable zone with such an instrument. So that is already, I mean, it sounds like too simple of a criteria, but it is helpful to rule out quite a few targets in order to focus on the ones that are potentially relevant. So of course, both in the, I would say both in the retrieval, atmospheric retrieval part, and also in the detectability computations, in order to go full real life, I mean, we'll have to introduce additional criteria, but this was a way to get some boiled down results.
Awesome. Thanks. Avi?
Hey, yeah, Oscar, great presentation. Really exciting work overall. I was really intrigued, of course, by the power, and I mean, we knew this, but it was great to see it worked out, the multi-phase measurements, which I think, especially for hydrogen-rich planets, where you don't expect a significant phase-dependent variation in albedo or properties for these cold planets. That sounds very effective in trying to break degeneracies. But I really liked the then analysis of the Roman targets, but how many Roman targets can we get multiple phases or the sufficient phases to break those degeneracies? because those phases obviously are dramatically different, as you pointed out, that's necessary, and yet we're severely limited by the contrast and working angle, right, for Roman. So are there anything, will we be able to do that effectively
So-
for any Roman periods?
Yeah, I mean, I agree. It's a good question. I think Roman itself will not be able to get the full range of phase angles, but if we do the same computation, say for habitable worlds, we might have some exoplanets for which Roman will be able to cover some of the phase angle space, and then we'll have another mission that will be able to go to better contrast levels, implying higher phase angles. So I think Roman will be great. I mean, I think I have a backup slide on that, but this is the type of table that we get in the paper, in this paper in which we apply the code to Roman. But unfortunately, I'm just showing here the pessimistic scenario for the coronagraph. So this is this is not the most exciting one, but these are the results for each of the three filters, and you can see these are the range of phase angles that we get. So we will be getting close to full phase and potentially close to quadrature for some exoplanets. If we go to the whole, I'm just trying to go through the paper and check some numbers, but if we go to the excellent performance scenario, we have quite a few planets for which we have phase angles greater than quadrature potentially detectable with Roman. Mostly, I have to say, at the shorter wavelength filters. So probably not at 800 nanometers, but at 500 and 700 nanometers, we could go. I'm seeing here 116, 117 for several exoplanets. So I really invite you to have a look at the paper, at this Roman paper, because I cannot. I might share the screen if you want to show you. Let me quickly do that. I don't want to just say, yeah, go to the paper. I don't know if you can see the paper in here.
Yes. Yep.
Okay, so this is the optimistic scenario, the same that I was showing you before, and we have some papers, some planets, say Upsilon Andromedae D, for which in this blue filter we have 70 to 120, 90 to 120. So we'll be able to probe some high phase angles. Whether we will be able to probe some low phase angles for the same targets will be a whole different story. So you can see here in these histograms the range of observable phase angles. We have some interesting targets, but Roman will not only be a tech demo for hub worlds, it will also perform the observations that hub worlds will complete. So we will have the full orbital coverage when we have both missions.
Great, thanks.
So
Thanks.
I'll go back to the
Thanks,
I'll
Oscar.
go back to the presentation.
Somal, did you want to read off your question? Do you want to ask it?
Okay. Yeah.
Sure, yeah, can go ahead. Yeah, thanks for the wonderful talk. So I'm just curious,
Thank you.
what are the simulated exposure times for the multi-phase observations?
So we're actually assuming a signal to noise of 10 for each observation. This means we didn't have, like, both back then and today. I don't have a noise simulator for Roman or for habitable world, so I just assume signal to noise of 10. And whether that is feasible in a reasonable timescale will have to be checked with a specific code for that, right? So
Right,
yeah, you're right that increasing exposure time will improve the constraints on the atmospheric parameters. However, we repeated the multi-phase retrievals. So this same study, we repeated this by doing, say, 37 degrees at twice the signal to noise ratio, or 5 times the signal to noise ratio, and it was still better to actually go to combinations of of high and small and high phase angles at signal to noise 10. So it is really the backward and the forward scattering components that will start breaking all those degeneracies.
All right. Yeah. Thanks.
Thank you.
I don't see too many other hands, so I'm going to kind of pull right here and ask one more question, Oscar, that maybe is a thinker for you. And actually, it's something that Somal and I have been working on. So this kind of multi-phase retrieval is really powerful at understanding these atmospheres and surfaces potentially. As you start to drill down, and Avi kind of alluded to this, to smaller planets that might be hopefully more Earth-like, the issue becomes then that you might have intrinsic variability due to, weather, all these other things. Have you started thinking about, well, how do we crack that with life? And, are there potential ways with life plus, HWO that might be worthwhile? Are there specific phases? Are there specific techniques? Are there specific wavelength bands,
I mean, that's a very good point. I'm starting to check the effects of atmospheric variability, whether different types of atmospheric perturbations would be detectable with a reflected light instrument. That at least to check at which point the assumption of we're observing the same atmosphere at different phase angles is reasonable. Probably not too much, but we have to check which type of storms will actually change that pixel-wise, because it will be a pixel after all. So what type of perturbations will actually have an impact of the global albedo of the planet? That's a very important follow-up study, actually. Yeah. Somebody have a look at that. Yeah.
So we definitely have multiple people here looking at that from a different direction. So it'd be fun to talk to you. I was talking to Oscar about this before. If you see him at a conference, talk to him, pick his brain. He's happy to talk to you about all this stuff.
Yeah. We're discussing about how this like being in Europe, the US, like oceans are a bit of a boundary. So if somebody is in potentially Exoplanet 5 or in another conference, I'll be very happy to discuss about this.
Awesome. So can if everybody doesn't mind, let's give Oscar a hand again. Great talk, really interesting and prompting a lot of discussion and thought on this. And we, hopefully we'll see you around, Oscar, and we can kind of see more exciting work from you in the future.
Cool. Very happy to discuss with you. Thank you for having me, actually.